Hey, Physics 30, so I'm going to go over worksheet number 3 here. Just a simple refraction here. So what's the speed of light in crown glass? So you just have to remember that there's a formula for this index of refraction stuff. It's just a simple ratio between the speed of light and how fast it's actually traveling. So I can just rearrange that equation. I can get C is equal to, or V is equal to C over N. And that'll just be the speed of light, which is 3 times 10 to the 8. It's on your formula sheet. You can always find that there. I'm going to divide it by the 1.5, 2 number here, and we're going to get 1.27 times, no, sorry, 1.97 times 10 to the 8 meters per second. So slower than the speed of light. You can never go faster than the speed of light. In this case, I was just looking for the angle of refraction as a ray of incidence is incident on a quartz block. So I'm just going to say the quartz block is one down here. I have a ray of light coming down, hitting that one with an incident angle of 35 degrees. I'm just going to list everything off here. We're going to make an assumption it comes from air. Okay. If it does that, most likely it's going to bend towards the normal. We're looking for that angle there. So let's just label the top 1, the bottom 2. Since I'm looking for 2, I'm just going to put theta 2 on the top over theta 1. Now just remember that the index of refraction switch over. So I'm going to put 2 on the bottom here so they're across the formula from each other. And then I'm just going to put the numbers in now. So let's say 35 degrees, making sure your calculator is in the right mode. Quartz, we decided, was the 2 in this situation, and air is 1. And we just rearrange that for sine theta 2. So 1 divided by 1.47 times the sine 35. So now I haven't done the sine inverse yet, so this is just before that. So the ratio that we get, sine ratio, is 0.3902 blah, blah, blah. Then I'm going to take the sine inverse of both sides, sine inverse, and we get 23.96 degrees. So 22.96 is going to round up, kind of chain react, and we get our refractive angle. Yeah, it looks like it bent towards, yeah. It was 35 originally, now it's 23. All right, so light enters into a ruby at an angle of 25 degrees, so it's very similar to one we just did. We're going to just make the assumption it's coming from air. It's going into the ruby. Its N value is 1.54. It's going to come in at an angle of 25 degrees. It's going to probably bend towards the normal, more than the other one too, because the other one was only 1.47. So I'm going to set up the same equation. Call this 2, this 1, 1. So I'm going to do sine 2 over sine 1 is equal to n1 over n2. I'm going to solve for sine 2. Oh, it seems like I haven't put any numbers in yet, so oops. I can put the numbers in now, and I could just kind of skip the sine inverse step here. So I'm going to go n1, which we decided was air, times sine 25, divided by 1.54. Take the sine inverse, and we get 15.9 degrees. 15.9 degrees. I had to shortcut that a bit because I'm running out of space. Now we're going to determine the wavelength of ruby light. Now there's 2 ways to do this. The wavelength of the light in ruby. It's 540 outside this. So there's a few different ways to do this. I'm going to use the sine or the Snell's law to do this, where we know the index of refractions, N2 and N1. Let's keep the same picture up here. I'm just going to label my wavelength out here. And then over here I got lambda 1 and lambda 2. And we're just going to rearrange this to get lambda 2. This is the wavelength. So times lambda 2 up. So I got n1 lambda 1 divided by n2. Okay, n1 was 1. Lambda is 540 nanometers divided by 0.54, and we get 3, how many sig digs we need? 3 sig digs here, so 351 nanometers. Okay. What's the speed of light in the Ruby? Maybe I should just specify that. We could just use what we used in the very first equation there, or I can use this ratio again. This time put V's instead of lambdas. So it'll look very similar. N1 times V1 divided by N2, which ends up working out the same way because V1 is the speed of light times 1 divided by the 1.54, and we're going to get 1.95 times 10 to the 8 meters per second. Okay, and what's the frequency of light in the Ruby, out the Ruby? It really honestly doesn't matter because the frequency stays the same. So if I know the wavelength somewhere, which we do, we know the wavelength is 540 nanometers. This is in air. And the speed of light in air is 3 times 10 to the 8 meters per second. I can use the universal wave formula here to find out what my frequency is. So I'm going to take my speed, 3 to the power of 8, divided by the nanometers, but I got to change that into meters. So remember what to do with that. I'm going to change that into meters by timesing this number by 10 to the negative 9. You do that in your calculator, moves the decimal place over and gives you times 10 to the negative 7. But this is not the proper scientific notation, though. Punt those two things in my calculator there, and I get 5.56 times 10 to the negative, or positive 14 hertz. There you go. Looking pretty good. I'll see you in the next video. Bye.